All right, we are still in Chapter 6. We're looking at some practice problems in AP Stat. Trying to go through to show you as many examples as possible to help you along your way and your journey here. So, we are in the end of Unit 1, trying to wrap it all up. After these practice problems, I'll give you some general practice problems as well to help you review for your exam. But for your Unit 1 exam, I should say. The first, take a look here again. If I'm going too fast, make sure you pause these videos and write the problems down if you want. But it says the first stat exam had a mean of 80 and a standard deviation of 4. The second had a mean of 70 and a standard deviation of 15. And it says Reginald scored an 80 on the first test and an 85 on the second. Sarah scored an 88 on the first, but only a 65 in the second. Although Reginald's total score is higher, Sarah feels she should get the higher grade. Explain her point of view. Well, same idea as the last problem. All right, as you're looking at this, the first one had a mean of 80, a standard deviation of 4, and the second had a 70 and a standard deviation of 15. Reginald says he got an 80 on the first test and an 85. So his z-score in the first one, that's easy, 80 minus 80 is 0. But then the second one was 70 and 80, so then it would be 10 divided by, sorry, not 10 here. He got an 85 on the second exam. And the mean was 70, so when he subtracts those for 15, divides it by the 15 there, he would get 1. So basically 0 and 1, Reginald totaled a 1 with both of his z-scores on both. For Sarah, though, when she was doing this, she was 8 over divided by 4, which is a 2, so she got a z-score of 2. But on the next one, she had a 65, and that test had a 70 as the mean. So when she subtracted, it was a negative 5 divided by the 15, so it's negative 1/3. So when she totals her z-scores up, her z-score was actually higher than him. While her raw score is definitely lower, her z-score is higher, so she could argue that she has a higher z-score and should technically have a better grade because of that. Taking a look at this, Anna, a language major, took final exams in both French and Spanish and scored 83 on each. Her roommate Megan, also taking both courses, scored 77 on the French exam and a 95 in the Spanish exam. Overall, all right, the students' scores on the French exam had a mean of 81, a standard deviation of 5, and the Spanish scores had a mean of 74, a standard deviation of 15. To qualify for language honors, a major must contain at least an 85 average for all language courses. Does she qualify? All right. Would the student qualify, and which student's overall performance was better? So, Anna's average, right? It says Anna took final exams in both French and Spanish and scored an 83 on each. 83 divided by 2, 83. There's her average. She is an 83. Megan, it says, she took them, scored a 77 and a 95. She averaged 86. So technically, her average, it says, to qualify, needs to be at least an 85. So right now, if we did an average, just straight up, that's what it looks like with Megan, right? Qualify, not qualify, just straight up. All right. So if we were to look at it like that, that's what we got. But which student's overall performance was actually better? So that's why when you're looking at this on the exam, though, the mean was 81, standard deviation of 5. Anna's score of 83 was 2 points, or 0.4 standard deviations above the mean. All right. Megan's score of 77 was 4 points, or 0.8 standard deviations above the mean. So on the Spanish exam, if you were to look at this, the mean was 74, standard deviation was 15. Anna's score of 83 was 9 points, or 0.6 standard deviations. Megan's score of 95 was 21 points, or 1.4 above the mean. So measuring their performance in standard deviations is the only fair way in which to compare the performances of the two women on the test. Anna scored 0.4 standard deviations above the mean in French and 0.6 standard deviations in Spanish, for a total of 1 above the mean. All right. So taking a look at this, Megan's scores are 1.4 standard deviations above the mean. So what we're getting at is who actually did do better. If you take a look at the standard deviations and look at it that way to see, instead of what they had to get on the test, they're just getting at that. You see the difference. You look at it and you say the one is qualified, but technically the other one could also be qualified because Anna scored 0.4 standard deviations above the mean in French and 0.6 deviations in Spanish, for a total of 1. Okay, so she was 1 standard deviation above the mean, as opposed to Megan, who scored 1.4 standard deviations above the mean. They both did well. And if the averages on them were, in general, you're saying they had to score above an 86. Well, what if the averages were, which they were, let's see, the mean was 81, and what was it on the other one? Sorry, oh, it's up here. The Spanish is 83, and she, let's see, took final exams of, scored 83 on both. Her roommate scored 77 on the French exam. Overall, student scores on the French exam have, all right, the French was 81, she scored higher than the mean, and the Spanish was 74, so she scored way above that. So the point is, she scored better than everyone else, but because she didn't get an 86, she's not allowed. She scored 1 standard deviation above the mean. That's great, that's fantastic. Even though hers is 1.4, she still scored above it. That's the idea here that they're getting at. Maybe it's a different way of looking at data to decide who gets what. A town's January high temperatures of 36 degrees Fahrenheit, standard deviation of 10, while in July the mean high temperature is 74 and the standard deviation is 8. In which month is it more unusual to have that? Well, to look at the more unusual idea, it says 36 degrees of the standard deviation of 10 is the average, while in July the mean is 74, standard deviation of 8. So in which month is it more unusual to have a day with a high temperature of 55? So if you have a high of 55, you plug it in. 55 minus 36 divided by 10, 55 minus 74 divided by 8. So when we do that to see what we get, in January with mean temps of 36, standard deviation of 10, a high temperature of 55 is almost 2 standard deviations above the mean. So it's 2 above. In July, with mean temperature 74 and 8, a high temperature of 55 is more than 2 standard deviations below the mean. So a high temperature of 55 is less likely to happen in July when 55 is farther away from the mean. You just got to find the standard deviations, which one is farther away from the mean. That's all you have to do. 2 companies market new battery targets at owners of personal music players. Duratunes claims a mean battery life of 11 hours, while Rock Ready advertises 12 hours. Explain why you would also like to know the standard deviations of the battery lifespans before deciding which one to buy. And then also suppose those standard deviations are 2 hours for this one, 1.5. You are headed for 8 hours at the beach. Which battery is most likely to last all day? And if your beach trip is all weekend and you probably will have the music on for 16 hours, which battery is more likely to last? So taking a look at this, it says standard deviations measure variability, which translates to consistency, right? So a type battery with a small standard deviation would be more likely to have lifespans closer to the mean. So then if I know that the standard deviation is small, then I can guarantee the likelihood of my battery life is pretty close to their average. However, if they're using average lifespan but their standard deviation is large and spread out, I would rather hear about the median battery lifespan more than anything, if that makes sense, if it's larger away. So that's why it's important to know what you're looking at with your data. Now it says the Rock Ready battery has a higher mean lifespan and smaller standard deviation. So they are the better battery. So it says suppose a standard deviation of 2 hours is for the Dura time. So 11 divided by, it claims it has a 11 over 2, and you're going to the beach for 8 hours, right? So if we wanted to find this, the z-score, the c, we would take the 8 minus the 11 hours for theirs, divide that by, what did it say the standard deviation was? Suppose it was 1.5, 2 hours for Dura, so divide that by 2, and yeah, we get Rock Ready is 1.5 below the mean. And if we do this one of 12 hours as advertised, so we want it for 8 hours, 8 minus the 12, and then divided by the standard deviation, which it gave us as 1.5, which is the negative 2 2/3 down the line. So this one, the standard deviation below the mean. So Dura batteries are more likely to fail before the 8 hours have passed, basically. 8 hours is 2.3 standard deviations below the mean lifespan, and rock ready is 1.5 standard deviations below. So it says right here, Duratune's batteries are more likely to fail before that 8 hours because they're closer to that mean. So we would probably want to go with the rock ready. It says 8 hours is 2 2.3 standard deviation below the mean lifespan of rock ready, and 1.5 standard deviations below the mean for Duratune. So we wouldn't want to go with that one. C though, if you're going for 16 hours, right? 16 hours is 2.5 standard deviations higher than the mean lifespan, because we would take the 16 minus the 11 that's claimed, minus 11, and then divide by the standard deviation that they gave us of 2, right? So that's how we get 2.5, and 2 2/3, right? We take the 16 minus the 12 divided by 2, so 16 hours is 2.5 standard deviations higher than the mean, all right, and 2 2/3 standard deviations higher than the mean lifespan for rock ready. Neither battery has a good chance of lasting 16 hours because anything within 2 standard deviations is usual. They're both unusual and outside. So, but Duratune's batteries have a greater chance, because right here it says, but the Duratune's batteries have a greater chance than rock ready of lasting within the 2 hours, or sorry, within the 16 hours than the rock ready, because the rock ready is even farther away from that. That's what closer to the standard deviation of the mean. Sorry. Anyway, trying to race through that there at the end, that's why I got a little jumbled up here. So when we come back, we can dive right into this example.